What I'm hoping you noticed in this video is that when we went downhill, we gained energy, we went faster, and when we went uphill, we used energy, which caused us to go slower. This same principle underlies the electron transport chain, and I'm going to explain how in just a second. So let's take a second and remember what we've made so far in our processes of cellular respiration. First, in glycolysis, we managed to make 4 ATP and 2 NADH. However, during that process, we spent 2 ATP. So net, we have 2 ATP and 2 NADH. During pyruvate processing, we made 2 more NADH molecules. Then we got to the citric acid cycle. In the citric acid cycle, we made 2 ATP, 6 NADH, and 2 FADH2. If those numbers seem weird to you, remember we broke our sugar into 2 3-carbon sugars, so a couple things get done twice. So at this point, what this means is that we have 10 NADH and 2 FADH2. Well, what are we going to do with those? We're going to use them to make some ATP. Please note that this process is occurring in the inner membrane of the mitochondrion. As I move this NADH, which now has those extra electrons on it, we're going to bring it up to complex 1. In complex 1, those electrons are going to break off, and the energy from that reaction is going to be used to pump these 2 protons across the membrane. These electrons are moved through the electron transport chain using a series of oxidation and reduction reactions. Remember, whenever we oxidize something, we have to reduce something else. The removal of these electrons from these complexes releases some energy. That energy is used to move the protons. Those electrons will continue to be shuttled down the electron transport chain by Q, the next complex in this sequence. Q will shuttle those electrons towards complex 3. In complex 3, again, those electrons will be used to supply energy to move protons or hydrogens across the membrane. When this happens, those electrons will continue to be transferred down their energy gradient by cytochrome C, and they'll reach complex 4. At complex 4, again, their energy will be used to transport hydrogens across the membrane. At the end, those hydrogens go down their gradient through ATP synthase. In doing that, they supply the energy needed to add a phosphate to our ATP or ADP, making it into an ATP. That oxygen by complex 4, it's the final electron acceptor, and that means that it's important to this process. While this reaction can occur in the absence of oxygen, one of the problems is that since oxygen is the final acceptor of the electrons in the electron transport chain, if we don't have oxygen, we'll get a buildup of electrons. Ultimately, this buildup of electrons makes it harder to oxidize and reduce the things we need to oxidize and reduce. And this means that eventually we will no longer be able to create ATP, as we will no longer be able to oxidize the NADH, taking its electrons and turning it into NAD. For each of our NADHs, we're able to make 3 ATP using this process, so long as oxygen is present. And you might think, well, what's up with the FAD then? What does it do? Well, it turns out that FAD doesn't bind to complex 1, but rather binds at complex 2, and that's where its electrons get shuttled to Q. It can still be used just like NAD to pump out protons, but since it started a little further down the chain, it only does 4 protons instead of 6. This means that it can only produce 2 ATP for every FAD H2. Okay, so let's summarize this process. Basically, what happens is you've got these NADHs. They've got extra electrons, and what they're going to do is those electrons are going to kind of pop off of them and join enzyme CoQ. When that happens, we get protons that shuttle across complex 1. Those protons, or hydrogens, are going to build up because once those electrons are on CoQ, they're going to go down, they're going to end up on cytochrome C. Once they're on cytochrome C, we make more energy, we pump more protons out. And in the end, what happens is all those protons we pumped out are having a moment like in The Godfather. They're saying, once I get out, they pull me back in. What happens is they want to go back in. And we use the fact that when they're going down their concentration gradient, they're creating energy, just like us going down that roller coaster earlier. They're moving. That's the direction they want to go. And we use that to power the ATP synthase that's going to be putting phosphates onto ADP. This is a little more efficient for the NADs because they can start at a little bit higher height, basically, in the energy game. And because of that, what that means is that for every NAD, we get 3 ATP, and for every FAD, we only get 2. Now, let's do some math. Since we started with 10 NADs, that means we get, on average, 30 ATP from those NADs. And since we start with 2 FADH2, that means that we get 4 ATP from those. So in using this process, we've generated 34 ATP. Now, in addition to those, we have the ATP we generated earlier, 2 from glycolysis and 2 from the citric acid cycle. So that means round about 38 ATP. Depending on the book you look in, the number might be a little bit different.